All right. Welcome back, everyone, to the next in our series of thematic talks for the winter school. And this today's theme has been discussing kind of confirmatory relations in science, relationships between theory and evidence. And following on that theme, we're going to have a talk with a broad idea from Professor Michael Strevens. Professor Strevens is a professor of philosophy at New York University, and he has written a number of excellent articles and a number of excellent books as well on a wide range of topics in the philosophy of science, on explanation, which we discussed yesterday, on probability, and the most recent book is on the kind of logical structure of knowledge gathering in science, or more precisely, maybe the illogical structure of knowledge gathering in science. And he's going to be, I think, touching on a few themes from that book in his talk today, which is entitled The Illogical Logic of Science. So I'll hand it over to Professor Strevens. We'll have a 45-minute talk and then questions from all of you.
Great. Well, thanks very much for inviting me to give this talk. It's one of the great things about Zoom is doing these kinds of events. So I'm very happy to be here talking to you all. This is a talk about, in a way, how brilliant science is. It may look from the title as though I'm about to critique science, but that's really quite far from the truth. These ideas are taken from my book that I wrote for a more general audience than philosophers, but which still contain a number of philosophical ideas that I haven't published elsewhere. So I hope the book is also of interest to philosophers. In any case, if you're interested in what I'm saying and want to hear more about it, then this book, The Knowledge Machine, is the place to go. So my topic today is, or perhaps isn't, evidential support in science. So this is the topic you've been discussing all day, and so I hardly need to illustrate it with long disquisitions or complex examples. The basic question is the question of how evidence bears on theories. And in particular, if we focus on what's often called the evidential support relationship, then the question of whether evidence supports some theories more strongly than others, or whether it undermines them. It seems this is a question that has to be settled if science is going to do any of its wonderful work. It's at the very bottom of our use of evidence in science to sort through theories and ultimately converge on the most successful and, we hope, the truest theories of the world out there. The philosophers often talk about evidential support under this code name, which makes no sense to the rest of the world, confirmation theory. But confirmation theory, as I expect most of you know very well, is the philosophical theory, or attempt to develop a philosophical theory that lays out the facts about evidential support, that tells us to what degree any particular piece of evidence supports a theory or undermines a theory. Now, there's been, in the last 50, 100, 150 years, a lot of confirmation theory has been done by philosophers of science and by philosophically or just methodologically self-conscious scientists, taking, I would say, either of two basic approaches. On the one hand, there is what you might call, although this is probably not a term most people working in this area would use, an anthropological approach to confirmation theory, by which I mean an approach that simply looks at the way that evidential support actually manifests itself in scientific discourse. So go to the scientific journals and see what criteria are used to decide the question of whether a piece of evidence is supporting or undermining or whatever, and record those facts. So it's almost like doing the ethnography of scientific epistemology. A philosopher who I think very, very influentially, at least for a while, took this approach is Carl Hempel. Of course, Hempel is famous for being a logical empiricist, but in his most famous work on logic and confirmation, his technique, if you look at it carefully and with open eyes, is although very much sensitive to questions about philosophical questions, is fundamentally to figure out what the scientists themselves are doing. The alternative to an anthropological approach is a logical approach, which in its purest form entirely ignores the way that scientists talk and just tries to construct or reconstruct the principles of confirmation of evidential support from first principles. And in the literature on confirmation theory, you'll find this approach is taken by many Bayesian philosophers of science, especially those who want to establish the a priori validity of the basic tenets of Bayesianism. Now, of course, it's not necessary to be entirely exclusive in either case, and many Bayesians who start out attracted by the logical force of Bayesianism are also concerned to argue that scientists, in fact, more or less follow the contours prescribed by Bayesian confirmation theory. And likewise, a philosopher like Hempel, who starts from the way that scientists think about simple evidential relations, also is concerned to impose a kind of a logical regimentation on what scientists are up to. But still, I think we can distinguish these two basic focuses and put Hempel in particular, who I'm about to talk about at some length, more in the anthropological camp. So for Hempel, it's a kind of, I think, non-negotiable that confirmation theory capture the way that scientists actually think about evidential support. Okay, so let me go on to talk a little bit about Hempel's theory that was developed, or at least there was the ideas were published in the 1940s, a long time ago now. Very influential for a few decades, but now often regarded for reasons that we'll very much be getting into as something of a historical curiosity. Maybe that's a little bit strong because Hempel is almost a kind of a secular saint in the philosophy of science, and calling his ideas just a curiosity seems therefore a little bit sacrilegious. But that is nevertheless, I think, the way they're often treated as at least as a, if not, maybe this is the right term when we're talking about a saint, as a kind of historical relic, rather than a kind of a live tradition to be drawn on as work on confirmation theory continues into the 21st century. Anyway, enough of that. Let's get into the theory and the way it works. So Hempel's theory is often called an instantialist theory, meaning that it focuses on the simple idea that at bottom, theories are confirmed by their instances. Okay. So instantialist just means turning on instances. Hempel says that a piece of evidence directly confirms a theory if it is an instance of the theory, and what I'm about to give you here is therefore his story about what makes something an instance of the theory. I'm just going to zero in on a very simple kind of theory that consists of a single hypothesis of the form all F's are G. Of course, real scientific theories tend to be rather more elaborate and maybe also in some ways messier, less precise than this, but there is something to be said for starting with a very simple example. And I'm just going to stick with this example, and it will be good enough for me to make the basic points that I want to. So Hempel says a piece of evidence is an instance of all F's are G, and therefore directly confirms it, that is, offers evidential support to it, under two circumstances. If it's either an F that is a G or a non-F. And it directly disconfirms that same hypothesis if it's an F that is not a G. Okay, so Hempel uses one of his examples is, of course, the hypothesis that all ravens are black. And an F that is a G in this case will be a black raven. That will be a positive instance and will confirm that all ravens are black. A raven that is white will be a raven, an F that is not a G, and that will therefore disconfirm the hypothesis. But direct confirmation is not all that's going on in Hempel's theory. There is also indirect confirmation, which I will just mention relatively briefly. A piece of evidence indirectly confirms a hypothesis if it directly confirms another hypothesis that logically entails the hypothesis in question. So to give you an example, again, going back to ravens, and here I get to show you a little bit of my amateur wildlife photography. This is in the White Mountains of New Hampshire, where I came across this black raven. And of course, the philosopher in me said, I need to record this positive instance for posterity. So here are my photographs for no particular philosophical purpose. But if we again go back to Hempel's example, hypothesis all ravens are black, then a black raven seen in the United States, like the one that I just showed you, is going to directly confirm the hypothesis that all ravens are black, because it is a raven that is black. It will indirectly confirm, therefore, anything entailed by that hypothesis. And so it will indirectly confirm all Australian ravens are black. Now, it's not itself an Australian raven, so it's not an instance of that hypothesis and not a direct confirmer of that hypothesis. But since all ravens are black implies that all Australian ravens are black, it's an indirect confirmer. Okay, that's enough of Hempel's theory to be getting on with. So here are some features of the theory. First of all, although I've been concerning myself with this extremely simple hypothesis of the all F's are G variety, one of the appealing features of Hempel's theory was that it gives criteria for being an instance and therefore for direct confirmation for a hypothesis of any logical form you like, at least in first order logic. Furthermore, Hempel solved, as he famously pointed out, a contradiction that turned out to be lurking inside a similar theory, a similar instance-driven theory of confirmation that had been proposed by the French philosopher of science, Jean Nicot. So it, on the one hand, it extended Nicot's ideas to cover hypotheses of any logical form, and then also repaired a serious problem that was lurking inside. And in these ways, it was a real step forward. It was also limited in some ways that Hempel was fully aware of. So first of all, it's entirely qualitative in the sense it doesn't say anything about degree of support. So it tells you that a black raven will confirm all ravens are black, but it doesn't tell you by how much. So it doesn't, for example, prescribe that the more black ravens you see, the less each subsequent raven will confirm the hypothesis, although this seems to be something we would intuitively want a theory of confirmation to do. And that's just because, or at least it's apparently because Hempel said, let's just get the qualitative stuff right first, and then we can flesh it out later. And that was a project he himself did embark on. But in any case, purely qualitative. Second, it in fact only allows hypotheses that concern observable properties to be confirmed, because your confirmer, your observation statement, as Hempel would put it, has to be couched in the same vocabulary as your theory. Therefore, your theory has to be couched in observational vocabulary. This is certainly a serious limitation of the theory, and one that later philosophers who are also working in the instantialist tradition, such as Clark Glimmer in particular, tried to fix. Okay, some further things about Hempel's theory that may seem strange in various ways. One is very famously that since anything that's not a raven, according to Hempel, is an instance of all ravens are black, anything that's not a raven confirms all ravens are black. So for example, a yellow banana confirms that all ravens are black. And that property of Hempels' theory has been much discussed, still makes for entertaining classroom discussions to this very day. The Raven paradox, people now call it. Perhaps not exactly a paradox, but certainly a peculiar consequence. Another strange thing about Hempels' theory, or maybe you think a limitation, is that it ignores all of what might be called the super-empirical virtues. It's not really a totally standard name for the super-empirical virtues, but what I mean is virtues that are more holistic properties of a theory, such as its simplicity or its explanatory power above and beyond simply its ability to predict, its elegance or beauty, lack of complication, the fact that it uses relatively few parameters. These kinds of aspects of a theory, which it seems that many of us and many scientists regard as not just desirable, but in fact truth conducive, that is, that simpler theories are likelier to be true, for example, people often say, are simply not a part of Hempels' story. Finally, and quite troublingly perhaps, it ignores epistemic context, background beliefs, and so on. The Bayesian philosopher I.J. Good pointed to this fact and showed, by constructing an elaborate and rather artificial example, that there could be a case where seeing a black raven actually disconfirms all ravens are black, because it gives you evidence that you're in a place where there are many, many ravens. So seeing one gives you a reason to think you're in the place with many ravens, but also you happen to know that that very place that's so full of ravens contains just a few white ravens. And those kinds of elaborate pieces of background knowledge, it seems, can really make a difference to the way that we interpret evidence. To use a somewhat more real-life example, when a few years ago now, an observatory in Italy detected what seemed to be particles traveling faster than light, emanating from the particle accelerator at CERN. The reaction of most scientists was not to think, oh, Einstein's theories have been disconfirmed, but rather, well, there must be something wrong with the detector. Something has been miscalibrated, which in fact turned out to be the case, because they had their background knowledge of all of the evidence supporting the Einstein's theories, and in particular the aspect of the theory that was connected to the impossibility of faster than light travel, really weighed in suggesting that the problem was not Einstein, but simply the measurement apparatus. So to simply ignore epistemic context seems, well, kind of unscientific. All right, I'm going to focus on three of these properties, limitations, or oddities of Hempels' theory in particular, not including the raven paradox, as it happens. So not the yellow banana confirming all ravens are black, but rather these three. The fact that the theory is purely qualitative, it ignores the superempirical virtues, and it ignores epistemic context, each of which seems to suggest that it will fall short, unless it is significantly enhanced, it will fall short of giving a complete story about the way that evidential support works in science. Okay, so here is my rather radical claim, my thesis in this paper. It's that confirmation actually does work this way, as Hempel puts it. There's at least a sense, and I'll have to say a little bit next about, so the very next thing I'll do is explain a certain distinction that I'll use to qualify this thesis and make it a little bit more plausible. There's a sense in which confirmation in science, or the way that evidence is treated in science, really is purely qualitative, or at least it doesn't quantify evidential support. It does ignore the superempirical virtues, and it does ignore epistemic context. Okay, there's my claim. This is a surprising thing. I myself, just to digress for a moment, this all kind of came to me when I was teaching Hempels theory in an undergraduate class, and I was trying to make sense of Hempels' ideas and trying to sort of get the students to see that there was something interesting, or try to get them to think there was something really interesting was going on here. And I somehow found myself thinking, if you actually just look at the way that evidence functions in scientific papers, it's not so far off Hempels' ideas after all. Hempel, by taking the anthropological approach, stumbled upon a fact about evidential support, which even he himself wasn't quite willing to fully embrace, but which deserves a much closer look. Okay, so now the closer look. So the distinction I want to make, which is going to be crucial to understanding how this claim of mine could possibly be true, is between official scientific argument and, on the other hand, private scientific reasoning. Okay, so scientific deliberation, that is, scientists thinking about evidence and theory and the connection between the two, goes on in a lot of places. Here are a few of them, ranging from the very public, like a podcast interview, to the public and rather official scientific journals, to the very private scientists' own mind, just their own thinking about the connection between evidence and theory. And I want to divide these venues into two groups. One of the groups is this one, scientific journals and conference papers. I call what goes on in these instruments of communication official scientific argument, because these are the official records of evidence and its connection to theory. These are the places that scientists kind of lodge their results and the places that preserve those results for posterity. They are, if you like, the official channels of communication, as I put it here, and the official repository of scientific argument. Insofar as science has an institutional memory, which of course it does, it's because of what's recorded in the journals and the papers. So that's one category. The other category is everything else, which spans a real range of different venues, from the scientist's own mind, the most private of all of the venues, to informal conversations among scientists of the sort that you might see at a lab meeting, to the most, I suppose, the most public, or certainly the most widely disseminated, or widely disseminating channels of communication, when scientists write popular books, appear on television, write op-eds, do podcasts, and so on. But these are all unofficial, simply in the sense that they're not the official channels of communication. I'm going to focus on one in particular, just to make life a little bit simpler going forward, but also because I think it's probably the most important, namely the scientist's own mind. So scientists' own personal thinking about how evidence bears on theory. Okay, so I'm gonna focus then on a contrast between these two kinds of venues. On the one hand, the official venues, scientific journals and conference papers. I'll just say journals from now on to save a tiny bit of time. And on the other hand, the private reasoning that goes on in the scientist's mind. Okay, here's now to take this distinction and make it relevant to the claim I was making about confirmation or evidential support in science. Here's my thesis now made a little bit more subtle and a little bit more qualified. Each of these venues, and like I say, you can just focus on the journals versus the scientist's mind, each has its own distinct way of treating evidence. You might say its own evidential support structure. Okay, so there's not a single story about evidential support or about the way evidence is treated in science. There are two different stories, and which one applies depends on the venue for deliberation. Okay, so let's begin with the scientist's own mind. In the scientist's own mind, the relations of evidential support, the ones that are as it were, driving the scientist's reasoning as they ask themselves oh, in the light of this evidence, which theory should I accept or think are plausible, or should I pursue? Should I put more work into? Which should I put aside? What should I think about my rival's work? What should I think about this work in some other field, which looks like it might be relevant to mine, and so on and so forth. All of these decisions, which are so crucial to the way that science is done, are made according to a kind of a logic, if you like, of evidential support that does all the things that Hempels' theory of confirmation does not. These relations quantify the degree of evidential support. They do take the superempirical virtues into account one way or another, maybe varying to some degree from one scientist to another. And they take into account all the relevant aspects of epistemic context. So this private scientific reasoning is functioning in the way that modern confirmation theorists think confirmation theory should function, sensitive to all of these aspects of the epistemic situation, the context, the superempirical virtues that are widely thought to be important, and then using that context to quantify evidential support, to make distinctions between evidence that supports a theory just a little bit from evidence that supports it overwhelmingly, and so on. All right, so here you have what everything a Bayesian might want in a theory of evidential support in scientists' own thinking. However, in scientific argument, in official scientific argument, the science journals and so on, the relations of evidential support you find are unlike that. They don't quantify a degree of support. They ignore the superempirical virtues, and they ignore at least many aspects of epistemic context. So they look a lot more like the relations that Hempel theorized in his paper back from 1948 or so. Okay, so now you have a better idea of what I'm claiming. It's not that this stuff plays no role in science. It plays no role in a certain very important theater of scientific argument. Okay, so now I want to at least do a little bit to convince you, at least to illustrate my own reasons for believing that this is a viable claim to make about the scientific journals in particular. I'm just because there's limited time, I'm going to focus in on two of these three properties: the lack of any quantification of degree of evidential support, and the lack of any role for the superempirical virtues, such as simplicity and so on, to play. As for context, I'll just make a remark so as not to make this whole thing seem completely mysterious. Scientific papers, I think, do often supply an epistemic context. In that respect, they don't ignore it. They give an account of the way that measurements were taken, and they typically begin with a summary of work that other people have done in the same field. But what they don't do is make any attempt to bring in those facts about, they supply those facts about context, and scientists use them in their private reasoning, but they don't make any attempt to bring in the context in an attempt to actually calculate or to determine evidential support, or further to calculate a degree of evidential support. So the epistemic context doesn't come into evidential support itself, though it may very well be reported in a paper. Okay, so having said that, I'll put the context aside for now and turn to the other two, starting with quantification. Okay, I am saying that evidential support is usually, perhaps, and I would even go further and say virtually always not quantified in scientific papers. Now, there is a lot of quantification that goes on. For example, in a great array of domains and disciplines, where people are where statistical significance is very important. And in order to establish the statistical significance of your evidence, you have to do something like perhaps the most common and also the simplest approach to statistical significance, calculate what's called the p-value. So you do a certain formal technical calculation, the probability that the null hypothesis would have produced the evidence, and you report this value, and this quantification is very important. In fact, in many areas, the publishability of your research hinges on having a low enough p-value. Okay, so what you're doing there when you calculate the p-value, and also in somewhat more complicated ways do other significance tests, is you're calculating something like the probability that a certain theory, in the classic case, the null hypothesis, not the theory you're actually testing, but in other cases, it could be the theory you're actually testing. The probability that that theory, given certain assumptions, ascribes to the outcome. And this is something you might also, I think, find reported just more generally, even outside the context of significance testing in a scientific paper. So these calculations, these things are what are technically known as likelihoods. These kinds of calculations are everywhere in scientific publication. But as philosophers of statistics and philosophers of science more generally, I think, would pretty much all agree, p-value or other kinds of likelihoods are not themselves enough to determine a degree of support. To determine a degree of support, you have to add other things. For example, you would have to add some kind of number quantifying the plausibility of the assumptions that you're making in order to calculate that value. Okay, the auxiliary assumptions. And this is something that is simply not done in scientific papers. Maybe that's a little strong. It's not as if there is never any discussion of the plausibility of these assumptions. But what you don't see done is any kind of systematic presentation using, for example, some sort of Bayesian calculation or something like that, that draws upon the plausibility of the assumptions, rather than the standard procedure is simply to make some assumptions that you hope your reader finds plausible, and then to calculate the likelihoods given those assumptions, but not to do the full calculation you would need to do from the perspective of a Bayesian philosopher of science or someone like that in order to get a degree of support. So there are all these numbers numbers that are attached to relations between theory and evidence in scientific papers, but they are not numbers quantifying evidential support. So what you do find in a scientific paper then is this. First of all, of course, a report on the evidence, at least when it's as almost all scientific papers are when it's reporting empirical work. There are, of course, theoretical papers that are purely theoretical, that just they're focusing on evidence-based papers. A report on the evidence, the way it's produced, and also a report on the way that the evidence would be predicted or explained by certain theories of interest, given certain assumptions. And perhaps very often, this part of the paper will have numbers in it, but these numbers will be likelihoods, the probability of the evidence given a theory, given the assumptions, not quantifications of support. And then the actual degree of support itself, or the impact that the evidence has on a theory, that's something that's just left to the scientists reading the paper, a scientific paper, to figure out for themselves. Now, I think in some sense, philosophers of science all know this. And so when I say degrees of evidential support are not reported in the scientific literature, it's also something everyone knows. But I'd like to you to see it in a new light, which will emerge in the course of the rest of this paper. Okay, now on to the superempirical virtues, also ignored, I claim, in official scientific argument. And I'm just going to focus in again since there's limited time, on one particular superempirical virtue, namely theoretical beauty or elegance, whatever that is. So many scientists believe, and I'm just going to kind of go along with their belief, that a theory's beauty is a consideration in its favor. So a mild statement of this view would be something like this. ceteris paribus, all other things being equal, a more beautiful theory is more likely to be true. You can find some rather stronger statements of the same sentiment among physicists in particular, especially fundamental physicists, especially among Nobel Prize-winning fundamental physicists. Here are some samples. When you look at the Weinberg one, for instance, he's saying an ugly theory could not possibly be true. Ugliness, in other words, is a decisive refuter. That's a pretty strong statement. I don't know if quite how literally he intended it, but clearly Dirac, Gell-Mann, Weinberg, all quoted here, did think that beauty had some considerable probative power. It was something that was not just nice to have, but was actually telling you something about a theory's, the chances the theory is true. And here, because we shouldn't just rely on Nobel Prize winners, but we should also look to see what working scientists are up to. Here's a line from Brian Greene writing in The Elegant Universe, which I think basically gets the mindset of many physicists right. He's saying scientists are guided by beauty because they think more that beauty is a sign of truth. But he then goes on to say in the same couple of pages, aesthetic judgments, these same judgments, do not arbitrate scientific discourse. In other words, scientific discourse, judgments of relative beauty don't play any role in scientific discourse. And what he means here, I believe, is official scientific argument. That is just about, how, as he puts it here, how theories fare when faced with the hard experimental facts. Here, putting it in my own terms, beauty in a journal article, an official scientific argument, cannot be offered as a consideration in a theory's favor. It's simply ruled out by the rules for discussing evidential support in scientific papers as a legitimate consideration. So the only thing that counts is the kind of thing that Hempel was talking about: successful prediction or retrodiction, or the kind of retrodiction that I would call I call in my book shallow explanation, when you help yourselves to a few facts that you can only know after in the wake of something's happening, and show how a theory in the light of those facts does indeed make a certain prediction. So that it's just these relatively simple connections between theories and facts that count in the official scientific literature, and not any of the wider stuff, such as beauty, such as the other super empirical virtues. To kind of drive home this point, I like to point to the fact that there's actually something that's irrationally narrow about this. I think it's a good kind of irrationality, in the sense that it really helps science, it makes science work well. But there's still something about it which is technically irrational. So here's the situation, or at least if you take scientists' claims about the importance of beauty at face value, here's the situation. On the one hand, paying attention to the beauty of a theory is really helpful for figuring out what's right and what's wrong, or for kind of, as it were, laying down a path that takes you closer to the truth, swimming up the beauty gradient, if you like. However, in official scientific argument, the rules say we must pay no attention to beauty. So that means that official scientific argument, what goes on in the scientific journals, is ignoring what scientists themselves consider to be a really important, and also, I should say, readily available source of information about a theory. Readily available because these judgments of beauty don't require any extra work to come up with. But to ignore a potent, readily available source of information is to violate what philosophers call the principle of total evidence. Maybe that was Carnap's term. And therefore to ignore a fundamental principle of rationality. Okay, so this narrowness that many philosophers thought told against Hempel's theory of confirmation, or at least cried out for Hempel's theory to be enhanced in various ways to bring in, for example, the super empirical virtues. This narrowness is a narrowness we also find in official scientific argument itself. Okay, well, you might wonder whether public scientific argument, official scientific argument is just a kind of a mess. The real action is going on in the scientist's head, and what's in the journals is a kind of an unfortunate accident. I mean, that would be remarkable, but still, you would expect the journals to operate according to some kind of inductive logic. This is clearly what Hempel expected and what most confirmation, I dare say, perhaps all confirmation theorists coming after Hempel would expect. What you actually get is something that really is not a logic at all. You simply don't have an apparatus for quantifying evidential support. What you have is more like a kind of a report of the evidence and certain connections between the theory and evidence, but nothing that itself allows you, that prescribes any kind of any relation of evidential support. It's up to you to figure out what the relations of evidential support are using what's going on in your own head. Furthermore, not only is it not a logic, it's positively illogical insofar as it ignores beauty and so violates, and other superempirical virtues, and so violates the principle of total evidence. I think what happened with Hempel is taking the anthropological path, he picked up on some of this and replicated what was going on, the mess, as I pointed here. And you might think, okay, well, Hempel, here's a case where the anthropological approach was just a mistake, because by focusing on what scientists are up to in the journals, you get this kind of weird cultural accident almost, and you ignore what's really important and vital about scientific argument, which is what's going on in scientists' heads. So should we just forget about official argument and work on the logic of private reasoning, on the inductive logic, evidential support, and all that's going on in scientists' heads? I don't think so. The rules of scientific argument in the journals are doing something. I mean, first of all, and something that makes sense, they require scientists to report their evidence and to establish certain connections between theory and evidence. So they're very much connected to the intensely empirical nature of modern science. So it's worth investigating what's going on, whether you call it confirmation theory or not, in these rules. We might ask, what are the criteria for empirical evidence that determine whether something can be reported in a journal as a piece of empirical evidence or not? What are the procedures for putting it all together in a scientific paper? And ultimately, why did these rules exist? And I'm just going to say a few words to finish off about why the rules exist. So this is going to be just a glimpse of the story that I lay out in my book, The Knowledge Machine. Okay, the function of the rules of scientific argument. So these are the rules of official scientific argument, the rules that prescribe what can and cannot go into the journals, both positive, laying out what counts as empirical evidence, and perhaps more importantly, for the next few minutes, negative, saying what can't go in. I want to take what I think of as a motivational approach. So this has nothing to do with logic and everything to do with the human psychology of scientists. The rules motivate scientists to do something they wouldn't otherwise do. And in so doing, they enhance the power of science. That's the basic idea. I myself was inspired to take this approach by Thomas Kuhn, who lays out what I think is a really interesting version of a motivational story in his famous book, The Structure of Scientific Revolutions. Now, in Kuhn's story, I won't go into the details. Any piece of scientific research is governed by a paradigm, which is something like a complete recipe for doing science in a very particular way. How important different questions are, how you should go about answering the questions, methods, and so on. In Kuhn's telling, scientists can't imagine a paradigm failing, even though historically paradigms regularly fail. So I guess it's important scientists don't read history. But because of this kind of limitation or narrowness in their thinking because they can't imagine the paradigm failing. They're like all people who are gifted with the gift of total self-confidence, of a complete lack of self-doubt. They push ahead. They expect the paradigm to be able to solve every problem, and so they focus on fitting even the smallest details, smallest and most expensive to discover details into the paradigm, showing how it all hangs together. In so doing, they turn up precisely the details that ultimately overthrow theories. If you remember Kuhn's story, that bring about the anomalies that bring about crisis and ultimately revolution. So I'll use Kuhn's words here, by forcing scientists to investigate some part of nature in a detail and depth that would otherwise be unimaginable, unimaginable in the sense that scientists wouldn't devote themselves to the minute, expensive, tedious grind that's required to take some tiny little fact and fit it into the big picture. They actually find the tiny little facts that overthrow the big picture. And that's how scientific progress happened. Now, like many people interested in how science works, I think Kuhn exaggerated the extent to which these recipes for doing science, his paradigms, were really uniform and universal and had such a tight grip on scientists. So I think the Kuhnian story can't be quite right, but I love the story and I want to take it over for my own purposes. And I'm just going to super briefly sketch the way I do so. So I think it's not the paradigm, but the rules of official scientific argument, these rules that span all the different disciplines of science, and in fact that are common to all of modern science. These rules, the ones I've been discussing, and that include the irrational narrowness and all of that, are what force scientists to, again in Kuhn's words, investigate nature and a detail and depth that just simply wouldn't otherwise occur. The same detail and depth that is necessary for progress because it's what gives science its power to ultimately undermine the old theory and to bring in the new. These rules establish something like that. So remember, they don't apply at all to a scientist's own thinking, but then they turn the public scientific argument into what you might think of as a kind of a game in which you just have to publish your evidence. You don't have to establish any interpretation of the evidence. You don't have to calculate any degree of evidential support, and in which just publishing the evidence means not making any kind of other kinds of arguments, and in particular, any kind of super empirical arguments for your theories. So it's a game in which you win, if you like, or play and win by gathering together vast amounts of evidence that's significant by the standards of the rules, positive and negative instances of the hypotheses in question, to put it in a Hempelian way. What makes the evidence significant is something that's fairly straightforward to determine. It could be as simple as Hempels' story about something being an instance of the hypothesis, or more typically, it's something to do with significance testing, like calculating a p-value. That's it. That's all you have to do to make a move in the game. And because of this, the effort that is going into uncovering evidence is maximized. All of scientists' effort is going into digging up the evidence in just the way that Kuhn said. Okay, and so that's my story. That this kind of narrow and really only very partial attitude to the significance of evidence in the literature sets up this game that encourages scientists to maximize their evidence production, and then in their own minds they can bring in all of the richness that needs to go into thinking about evidential support to decide on the significance of this evidence, often disagreeing with one another, of course, at least in the short term, but ultimately pushing science forward. So the rules of scientific argument are, as I say, not illogic, and indeed, in a certain sense, are illogical, violating the principle of total evidence, but they nevertheless come together to play their part in making science this incredibly powerful theory testing machine. And so they play their part in making science the incredibly successful knowledge finding enterprise that we know it is. All right, thank you very much.
Thanks a lot, Professor Strevens, for an excellent and thought-provoking talk. I'm sure our participants have a lot of questions, thoughts they'd like to share. So yeah, if you have any questions, please raise your hand on Zoom. I'll come to you in the order in which I see hands raised. And the first hand I saw raised was Tushar. So Tushar, go ahead with your question.
Yeah, so actually, my question is quite messed up. There are a lot of things there. So yeah, certain points were there. You talked about that there's no quantification of plausibility of assumptions also, and you also talked about Green's statement where he says that aesthetic judgments do not arbitrage scientific discourse. But to second your claim, can I put another meta-mathematical argument? So here we are using quantification as a method. What if quantification itself becomes a test or evidence? So if you look at two different accounts, Indian mathematical accounts and say Western mathematical accounts. So there was Pascal triangle, coming out from a very, very different tradition. But we had, Meru Prastar Halayud, predating Pascal triangle by almost a millennium. Then we had, this Madhav Shrinkhala given by the astronomers in Kerala, which predated Taylor series by almost 2 centuries. And then there was also this thing, Pythagoras theorem versus Bodhayan Sutra. Now, these mathematical accounts converge. And these two mathematical accounts come from a very different, perspectives. The Indian mathematical perspective came from a purely aesthetic account of reality. And, so this mathematical convergence or congruence can itself not work as an evidence in favor of, aesthetic illogic of science or some kind of theory. And what does it say about your rules of scientific argument if mathematical convergence or congruence can be taken as an evidence?
Thanks. So let me begin by saying that this story about the rules of scientific argument in my telling really apply just to a single tradition, the tradition that began with the scientific revolution in Western Europe, and that then spread across the world as in the form of what you might call modern science. Certainly the way that science is conducted today in the various scientific journals around the world. So it's rather specific. The set of rules is rather specific. It doesn't apply to mathematics at all, and to the development of mathematics. And it only applies to a very specific tradition of inquiry, and not even to all of the kinds of inquiry that we might use the term science to pick out. So it doesn't apply to, say, ancient Greek science or Chinese science, or in fact to any form of science in any part of the world, except for this very specific tradition, which of course blew up because it was so successful at doing a certain kind of thing. So the kinds of traditions that you brought up are I think are not in fact legislated by these particular rules at all. Does that, now I'm not sure if that it completely answers your question though, but maybe it clarifies the way in which my own claim is confined in certain ways.
Yeah. So my point was, the way Newton treated mathematics. Even any scientist could make a prediction on the basis of certain mathematical apparatus or mathematical framework. So if different accounts lead to same mathematical framework, does it not substantiate your claim about the illogical logic of science?
I'm not sure if I caught all of that, but so you say, so of course, Newtonian physics and many other traditions in science make a lot of use of mathematics, although they're not themselves establishing mathematical truths. And then the second part of the question, maybe you could just repeat it.
Yeah. So exact calculus or exact mathematical framework, if has been produced by some independent theorizing, which is not even scientific, which is purely aesthetic. So does it know this congruence or convergence, of mathematics? Does it not bear upon these two different kinds of theorizing?
Well, that may very well be right. I'm not sure that anything I've said in this talk or that I say in my book really bears directly on that. As far as I can see, it's what I say sits quite happily with this idea about the convergence of different traditions of mathematical thinking. Are you thinking that there is some kind of tension there?
Yeah, maybe I'm not able to formulate my question properly. Because I see mathematics as the logic of science, in some ways.
Yeah. Well, of course, I mean, not just mathematics, but I think science is logical in many ways. There's just this, when I say science is illogical, I'm saying specifically with respect to ignoring the principle of total evidence. But in other ways, for example, in the calculation of likelihoods and p-values in particular, the mathematics all has to be done properly, according to the impeccably, in fact. So it's not as if there's some kind of wild disregard for logic. It's rather this specifically this narrowness is illogical by the usual canons of inductive thinking.
Okay, cool.
Okay, thanks, Tushar. Tarun?
Hello, Professor Strevens. Thank you so much for the talk. My questions are on humanity's knowledge machine, which of course you wrote a whole book about. And I must say, I was particularly thrilled to know that this talk was indeed about the illogical logic of science. I mean, I was actually wanting to talk about Bayesian confirmation theory, but I'm glad that you spoke about it because most of my questions are about it. So the first question is on, I'd like to know your view on a normative question that follows from the argument you laid out in the talk and in the book. Now, should science stick to this irrational constraint? Or, I mean, by science, I mean, should official scientific argument stick to this irrational constraint of the only thing that counts is empirical evidence? Or do you think official scientific argument should broaden its aperture and start considering other virtues as well, other super empirical virtues like beauty and simplicity?
Great, yeah. Excellent question. So I think so far things have worked out pretty well with the narrow constraint, what I call in my book, the iron rule. And one reason they've worked out well is because there is a way for aesthetic considerations and all the rest to flow into science, namely in private scientific reasoning. So a scientist like, say, Murray Gell-Mann, to just pick one of our pro-beauty physicists, is able in their personal thinking to take the power of beauty seriously and to assuming that what's claimed for beauty is really true, to as I put it earlier, swim up the beauty gradient, to zero in on theories that are especially fruitful or productive by following their nose for beauty. So we get it's not as if the power of beauty is completely ignored because individual scientists are not ignoring it. It's only ignored at this later stage when theories are put to the test. So we're not banishing, science is harnessing the power of beauty-guided thinking, even though it's officially kind of pushing it out of the discussion. And for that reason, it's not the handicap that you might have at first think when you hear my initial claims. You might think, well, that's terrible. We need to get beauty back into science, but it's there. It's just kind of hidden, as it were, or not even hidden really, because people like Gell-Mann and co were proclaiming its value to the masses in their informal lectures and books and so on. So I think the way the system currently works with these two in this kind of rather contrasting two different styles of thinking, the style that's in the literature on the one hand by establishing the rules of the game and providing a certain kind of motivational power, and then the much more wide open style in scientists' own minds, which allows them to take everything important into account. I think this has worked really, really well so far. That, of course, as they say, past performance is no guarantee of future success. Is it going to keep working? Maybe it's possible. Maybe with this technique has kind of, as it were, picked all the low-hanging fruit with, or most of it. It's many of the things many of the ways in which this particular slightly weird way of configuring inquiry, many of the ways in which it can be really successful have already been exploited, and we need to come up with new techniques. So some string theorists, for example, think that we need what they call a post-empirical physics, which will in fact allow considerations of sort of beauty-related considerations in the broadest possible sense, to do with unification, elegance, symmetry, and so on, allow them to enter into official scientific argument as well. And in certain areas, that could be a way forward. I mean, I have some half-formed personal opinions about this, but I'm not sure even how well informed they are. I do certainly think that we should be very reluctant to give up on this strange but extremely effective system that we have so far. And it's especially important to recognize that things which look dysfunctional actually perform an important function. I'll leave it there.
Thanks. Sorry, Tarun, did you want
Thank
to
you so
add
much for
something?
your wonderful answer, Professor.
Thanks, Tarun.
Thank you so much for your wonderful answer, Professor. I also have a few more questions. So should I ask them now, or is there anyone else who wants to ask?
There seems to be no one else in line at the moment. So I think you can ask other questions if you want again.
Okay. So Professor Strevens, I have another question. And for this, I must add a bit of context. The distinction that you draw between official scientific argument on the one hand, what is published in journals and what is discussed in scientific conferences, and unofficial scientific argument, which could be private or public, which is scientists' media appearances, scientists' own minds, scientists' conversations with their peers or graduate students or anyone else. So I like that distinction that you draw, because it clears up so many confusions that I had over the course of this winter school while I was learning about various ways of scientific reasoning and experiments and explanations. So given that distinction that you drew, assume that a philosopher of science, say me or any other philosopher of science, is now motivated by your work on this irrational constraint and sets out to ask real scientists if they're actually aware of the irrational constraint that their work is driven by. This may be a sociological study, maybe not philosophy, but let's say I'm going to ask real scientists. Let's say I'm going to go to a scientist and say, hey, scientist, do you know that what you publish in official scientific argument is actually driven by this narrow constraint of the only thing that matters is evidence? And are you aware of the fact that in your unofficial scientific argument, you pay attention to things like beauty and simplicity and so on? Is such a correspondence with a scientist, would that, let's say I were to record those responses for further work in philosophy, would those be official philosophical argument or unofficial philosophical?
You said official philosophical argument now, not official.
I mean, scientific. I mean, if I'm doing this for a philosophical study, let's say, not science then.
Yeah, so let's say we regard this, I talked about the anthropological approach. Anthropology is a science. So this is, in some sense, the science of science. We're doing empirical research into how scientists actually think. by examining the journals, or as you suggested, actually asking scientists themselves how they think about the way the rules work and so on. That would all be quite official. And it's, I mean, of course, science is bigger. We're talking about a research program, but then the results would be written up and reporting these facts. I hope that they would be reporting the facts, what I think are the facts, and that would be official scientific argument for sure. Yes. So scientists would be confronted with these facts about their discipline. But in some, I think many scientists, I mean, those passages I quoted from Brian Greene lay out the contrast pretty clearly. What Greene doesn't discuss is that this seems like a little bit, illogical.
Thank you for your answer, Professor. And one question, I'd like your confirmation on this, not Bayesian confirmation necessarily, but your confirmation on this. And that is, when I'm engaging with scientific work, contemporary scientific research, should I, when it comes to trusting science, should we trust only official scientific argument or unofficial? I think your answer would be we should trust official scientific argument, which of course, as you say in your book, is bound by this constraint.
Yes, I think the official argument is what we should look to, but precisely because it's impoverished in certain ways, it's not as if a regular person can simply look at the scientific literature and see to what degree the evidence supports a theory. So if they were on their own, they would simply have to recapitulate what individual scientists are doing in their own private reasoning, bring their own subjective probabilities, basically, for various auxiliary assumptions to bear and kind of make sense of it all that way. That, of course, is too much to expect. Even, first of all, just the range and complexity of the science on a crucial issue like the COVID pandemic, or even more so climate change, is too much for even a scientist who works in the field to take it all in personally. So what we really need, and what we have in some of these cases, in the case of climate change in particular, like where we have the UN panels, the IPCC, is a bunch of scientists who, as it were, kind of club together on behalf of the general public and read the scientific literature. So they're reading the official scientific argument, they're not consulting scientists unofficially, but then they attempt to supply something like what's necessary to turn it into to actually assess degrees of evidential support in a way that's not just purely autobiographical, but in some sense respects at least the weight of opinion. So there's a little bit of a sort of harvesting of the unofficial side, but as far as possible, just following what the official argument is saying, with the great basically handicap or burden that the official argument doesn't actually tell you what to think in the light of the evidence. So it's not an easy or straightforward job, and it's quite a bit of work to do it. In some cases, like the problem of climate change, it's clearly that so much is at stake, it's clearly worth doing it. But it does mean that ordinary people are left a little bit, under-resourced for dealing with, when it comes to following the science. It's, in some sense, it's something that can't be done without either a guide or a tremendous amount of personal work. And this is why we're all so confused about what we should eat and when we should sleep and so on, right? Because we have all of these different scientific reports that report somewhat contradictory results. And there is not, to some extent, government bodies like in the US, you have the FDA tries to interpret that and give people dietary guidelines and so on. But following the science, it's in part because official scientific argument works the way I say it does. Following the science is not an easy or straightforward thing to do. I either have to find guides and follow them, or put a lot of work into it myself, or just kind of muddle through and wait for some sort of consensus to emerge. all of these different options have their disadvantages, although we certainly wouldn't want to just start ignoring the science either.
Thank you so much for your answer, Professor.
Okay, thanks, Tarun. Aditya?
Yeah, hello.
Hi.
Thank you for the talk. So I have a question with regards to the evidential support part of your claim. So I feel like I might not be understanding exactly what you have in mind when you speak of quantifying evidential support, because it doesn't seem clear to me that this is necessarily not part of scientific journals. So for example, what I have in mind is take quantum mechanics. So it has various interpretations, say the Bohmian one or the Copenhagen one. And it seems pretty plausible that there are a bunch of articles which are discussing which of these interpretations suits it better. And in order to do this, it would naturally have to explicitly discuss how the evidence we have weighs in on each of these interpretations. So wouldn't that exactly be attempting to quantify evidential support?
Well, that's a tricky example because the Bohmian interpretation of quantum mechanics makes more or less the same predictions as various other interpretations. I mean, they're, at least insofar as we can determine for now. Maybe I should put aside that particular example and just talk more generally about scientific literature comparing various theories. Of course, what the scientific literature is trying to do is to give you the information you need to decide for yourself, to see that the evidence supports one theory over another. So it's certainly playing a role in this process. The question is whether it does so by actually giving you these quantifications of evidential support straight up. And I think that it doesn't. That what the scientific literature gives you is certain likelihood. So it says, I mean, in a typical case, if this theory is true, and if these assumptions hold, which would include some more general assumptions and also just some assumptions about the particular experimental apparatus that was used, that it was functioning properly and well calibrated and conditions were otherwise favorable, then this theory would predict such and such a thing. But we didn't actually find that thing. Okay, so that would be a classic scientific paper that would be, is the kind of paper you would naturally interpret as a disconfirmation of the theory, right? And so when you characterize it in those terms, you think, well, okay, so that paper obviously did quantify, say something very substantial about evidential support, namely that here's this piece of evidence that has a very powerful negative bearing on the theory in question. But look a bit, and the theory may well be the paper may well be treated that way by various scientists, maybe even by the vast majority of scientists will treat the paper as in a disconfirming way. But look at what actually is laid out in the paper, and I think you don't find anything that in itself lays out, sort of makes a claim of this overwhelming negative support. I mean, of course, the paper will point towards that claim. It will, as it were, turn your head in the direction that the author thinks it needs to be turned to take in the facts that will then, in your own mind, establish the evidence as a great disconfirmer. But it will not do everything that needs to be done in order to establish the disconfirmation. And in particular, and this sort of thing happens all the time with papers like this, it will leave open the question of whether the measuring apparatus really was performing correctly. It may give you evidence that that's relevant to that fact. We spent 3 days running tests and calibrating and so on and so forth, and that will give you some confidence that typically would give you confidence that that things are going well with that instrument. But again, it won't actually do any kind of specific calculation of the support that evidence gives for the auxiliary assumption that the measuring apparatus is working correctly. So again, as I say, it lays out lays out the facts that you need, and it may lay out all the facts that anyone needs, but it leaves it up to the consumer, the reader, to actually say, okay, this is good evidence that the measuring apparatus is working properly, and therefore the result that was measured is good evidence against such and such a theory. That's all happening in the scientist's head and not in the dialectic of the paper. And you can see, you can get a little bit of a sense of this by saying that you could disagree that you really have good evidence here without, strictly speaking, disagreeing with anything that's stated in the paper. You could say, okay, well, I believe you that you did all the calibration, and I believe you that the instrument produced this result, and so I don't disagree with, and I believe that given all these assumptions, the probability that the probability of getting that evidence given the theory is unbelievably low. I agree with all of that. Everything that you've said in the paper is correct. And nevertheless, I think something went wrong. Just because I'm really committed to that maybe the theory is very implausible, actually, or whatever, or it's very ugly. If I'm Weinberg and I think an ugly theory can't possibly be true. Sorry, very beautiful. Nevertheless, I think, despite agreeing with everything in the paper, I think something must have gone wrong with the instrument. That's my gut feeling. And therefore, this is not, after all, a serious disconfirmation of the theory. I can have that view without disagreeing with anything in the paper itself, which shows you that the paper itself did not make a claim about the degree of evidential support. Does that help?
If I can just have a quick clarification. So we saw in the case of beauty that it's not that discussions of beauty just happen to be absent in scientific journals. They would be treated as out of place and bizarre. So do you think similarly that discussions of how evidential support holds up to a theory or doesn't, do you think that they just happen to not be present in scientific journals, or that they would be seriously out of place and treated as unscientific if they were put forward in a paper?
Yeah, great question. So I think it's not exactly that there's a rule against calculating evidential support, but there are certain rules about rules that basically have the effect of it's not being laid out in scientific papers. Rules about that you might think of about the objectivity of what does go into a scientific paper. So the kinds of, ultimately, to calculate these degrees of evidential support, as I said, you need to have some sort of plausibility rating for various hypotheses, auxiliary assumptions at some point. Therefore, to calculate evidential support, you would have to report some sort of level of plausibility in the paper. But always, or almost always, these kinds of plausibility rankings are quite subjective in the sense that they can't be kind of just simply established on the basis of the facts that we can all agree on, and mathematical facts and logical facts and facts about derivation and so on. And what there is a prescription on, a prohibition on, is anything that's subjective in that sense. So in order to avoid the subjective stuff, scientists have to avoid bringing in precisely what they would need to calculate relations of evidential support, which does, which does have the positive benefit of making the whole question of what can be published and what can't a lot more straightforward and simple. It's just, you run the calculations, you get the p-value, your results are statistically significant, so technically the result is publishable. Of course, that doesn't mean your paper is automatically accepted, but it makes the rules of the game much clearer and more straightforward, and therefore turns it more into a kind of race for evidence than a rhetorical exercise in convincing people that this is the right plausibility ranking for this hypothesis and so on.
Okay, thank you very much.
Okay, thanks a lot, Aditya. Siddhant?
Yes, hello, Professor. Thank you for that talk. So my question might not be directly related to the talk that you just had, but you brought out the distinction between how scientists think themselves and then the official scientific literature. And you also mentioned that the general public is impoverished in terms of resources in how to interpret those official scientific papers. Now that reminds me of the HIV/AIDS activism that began in the United States in the 80s, where it was a group of activists and people who started going through the scientific literature, started educating people about what is there in the scientific literature, and then they conducted protests and stuff, and changing guidelines of how to conduct clinical trials for HIV patients and the drug delivery system, so on. So do you think there is this wide gap between scientific outreach or public outreach to the people regarding important scientific research, and should the official literature be somehow made accessible to the public in terms of because you have to, in terms of papers where it's related to health issues or like the climate change issue or the global pandemic, the research should be accessible to the people, and it should the official literature be modified in some terms in order to incorporate, because you have to translate that into policy decisions for the government. What are your thoughts about that?
Yes, well, that's a good question. I think my instincts are in favor of universal accessibility. My kind of liberal instincts are in favor of universal accessibility. What we've seen happen with the internet and all of that in the last 10 or 15 years has probably given a lot of us pause. Should maybe a little bit of information can be a dangerous thing, and it's certainly the case that it can be. It doesn't. Perhaps the truth doesn't always out in the end. I guess honestly, I'm not totally sure what to think. I still would incline, but I feel like this is as much personal prejudice and makeup as anything else towards making all of this information available insofar as possible, and allowing people, even groups of highly motivated groups, to kind of look through it and make their case, and hope that in the end there'll be enough guidance from those who have somewhat less motivated in their reasoning, so that people can make up their minds in a reasonable way. But it's certainly a danger, because the literature is so complicated. There are many ways to abuse that kind of access. And so I appreciate the dangers, and I'm not, to be honest, quite sure what to say at this stage about quite how we should deal with it.
Okay, thanks.
Thanks, Siddhant. Tarun, you have another question?
Hi, Professor. I have a couple more questions. The first one is on the Raven pseudo paradox, and so while stating Hempels' Raven pseudo paradox, you said that spotting one black raven somehow confirms the theory that all ravens are black. Why is that the case? I mean, how does spotting one black raven automatically confirm the theory that all ravens are black? What if in the future we might encounter, I don't know, green or yellow raven?
Well,
Not that we would in real life.
This is where the term confirmation is somewhat misleading. So when Hempels says it confirms all ravens are black, he means it's short for incrementally confirmed. So it gives you a little bit more reason than you had before to think that the theory is true. And it might be a very small a small increment of confirmation. If there were such a thing as the official logic of evidential support in science, it would tell you exactly how small. Instead, since there isn't, every scientist is simply determining for themselves how much weight they should give this additional black raven. Or in some cases, who knows, given their background beliefs, even taking the black raven as evidence against all ravens are black. But still, it would be okay in the strange way that the scientific literature works to publish this and count it as evidence in favor, even if well, maybe it's a little overcomplicated without some specific example, and most of the examples, like I.J. Good's example, are a little bit artificial. But you could certainly take the case of the particles that looked like they were traveling faster than light. I mean, essentially, nobody thought that this was evidence against Einstein's theories, as everyone thought something had gone wrong. But it was still okay, and therefore, in every scientist's head, the disconfirming power of this evidence was zero. It was just that something had gone wrong with the setup, and therefore there was in some sense nothing going on here. But nevertheless, it was absolutely okay to kind of report it in the official scientific literature as a piece of evidence that was relevant to the theory, because the fact that these powerful background beliefs just weren't relevant to determining the question of whether it counted as evidence or not. So that's not. So this is the kind of case where the way I think that the logic, the rules for publishing evidence really work. It's not even what Hempels says. So even in Hempels' qualitative logic, the raven is still a confirmer, but I'll put it this way, that a piece of evidence appears, as it were, in the supporting role in the scientific literature, doesn't even require the publication to establish that it's definitely a confirmer rather than just entirely neutral. So the faster than light particles counted as evidence relevant to Einstein's theory, even if taking the sort of background, the sort of most people's background beliefs into account, it wasn't really evidence against it at all. Maybe I should stop there.
Thank you for your answer, Professor.
Okay, thanks, Tarun. Tushar?
Yeah, so proceeding from this example, all ravens are black. So how would you treat Popper's hypothetical deductive model? What is your personal take on that in theory, confirmation, or distance
My take on the Raven paradox?
No, the Popper's account of hypothetical deductive model.
Hypothetical deductivism, he's asking.
So did you say Popper's account? Did I catch? Is that right?
Yeah.
Well, I think Popper got something importantly right, that scientific progress comes from theories ultimately collapsing in the face of bits of evidence, often small but very decisive bits of evidence. But I, like most philosophers of science, accept that a piece of evidence is never a kind of objectively definitive falsifier, because of the role of the auxiliary hypothesis always in bringing evidence to bear on theories, and the fact that different scientists just differ in what they think about the plausibility of different auxiliary assumptions. And in fact, that's precisely why falsification can, in effect, falsification can never be kind of, as it were, spelled out in a scientific paper in just the way I was describing earlier. It's always a matter of laying out the facts. If these auxiliary assumptions are correct, then this theory is definitely wrong. But then each scientist is going to interpret that fact in the light of their own personal feeling about the plausibility of those auxiliary assumptions. So science cannot be driven by deductive logic in the way that Popper hoped. But nevertheless, he was right about something very important. In its large-scale structure, science does proceed in a way that has that hypothetico-deductive pattern. In fact, I think Kuhn too believed this, which maybe sounds like a slightly surprising thing to say, but Kuhn too thought that theories ultimately fall down because they can't account for small facts. And that was a kind of it's not as if scientists are in their day-to-day reasoning applying hypothetico-deductive methods, because they're doing something, just trying to fit facts into the paradigm, Kuhn says. Likewise, I think, and so I wouldn't go that far, because scientists might personally be applying hypothetico-deductive methods in their own thinking, and they probably are much of the time, especially if they have a really strong sense of which auxiliary assumptions are right or not. So they might be personally thinking in a Popperian way, but the official scientific argument cannot reproduce those, as it were, falsification structures. Instead, it simply very suggestively lays out facts that many scientists will interpret as good reason to abandon a theory in the way that Papa hoped, although typically the process is rather less clear-cut than he thought, because there's typically quite a lot of disagreement about the auxiliary assumptions, especially when the science is unsettled.
Okay, thanks, Tushar. Tarun, you have another question?
Hi, Professor. It's me again, and I have one final question. So earlier today in today's philosophy of science class, I learned that scientists often have to make a trade-off between choosing a theory for its simplicity and fitting the evidence. And what I learned earlier today, before this talk, was that somehow simpler theories are usually chosen. Scientists prefer simpler theories over theories that perfectly fit the evidence, and that fitting the evidence is not the most important dictating virtue in scientific reasoning. Now my question is, now here I'm bringing in my newly acquired knowledge of the distinction between official scientific argument and unofficial scientific argument. So let's say a scientist has found two theories. One fits the experimental evidence perfectly, but it is far from simple or beautiful. It is very complicated and very ugly. The other theory, on the other hand, also fits the evidence, but not perfectly, not as perfectly as the complicated theory, but nonetheless, it fits. You could call that what in statistics they say line of best fit, where it fits most of the points. So the other theory, it more or less fits the evidence, but is nonetheless simple and elegant. So will a scientist choose the second simple and elegant, more or less fits the evidence theory, or will they choose the fits evidence perfectly, far from simple, far from elegant theory? And also, if they do choose the more or less fits the evidence theory, which is the simpler theory, which more or less fits the evidence, while publishing it in official scientific argument, are they merely going to say this theory more or less fits the evidence? And are they going to sweep the fact that it is simple and elegant under the rug? So is official scientific argument... this question relates to the decision scientists make in the unofficial space of their mind, and ultimately what they decide to express in the official sphere.
Mm-hmm. Great. Yeah. So how does a scientist... So the simplicity in this sense is one of these super empirical virtues. I think actually there's many kinds of simplicity, and some of them actually turn out to be more empirical. But let's zero in on the kind of case you're talking about, where it's just a matter of overall simplicity, and then even just stipulate that it's super empirical. So the scientists themselves think that simplicity is an important enough consideration that they favor this theory over the other. They publish this theory and show how it more or less fits the evidence. How are they going to manage the fact that they think that simplicity is really important here? You know, they want to fend off, as it were, the rival camp that has the more complicated approach that fits the evidence better. How do they play the game if they cannot, as I think they cannot, appeal to simplicity itself? So I do think it's important that they can't appeal to simplicity. I think if you look at the official scientific literature, and the things that may look at first like appeals to simplicity or parsimony turn out to be things that are in fact connected to the question of whether we really have evidence for a theory or not, rather than sort of the questions of simplicity per se. But of course, I can't elaborate on that right now. But so what that scientist has to do is the same kind of thing that a physicist who has their theory that they love because it's so beautiful will do. What they'll do is they'll display that simplicity. Okay, they're not going to sweep it under the rug. They're not allowed to say, "Believe my theory is better because it's more simple." You won't normally find that. I mean, this is human beings, so there are exceptions to every rule. But typically, you won't find anything like that. But what you will find is that simplicity is, they may point out that the theory is very simple in the way that someone like Gell-Mann might point out that his theory is very elegant. They don't want their readers to miss this fact. And of course, they want their readers to take this fact into account when doing their private reasoning. So they'll make it salient. if they're clever. They're simply not allowed, but while still not making, they still these, what you'll find the salience, it'll be unmistakable, but it will be done in kind of passing remarks, because what you typically cannot do, or what would attract the negative attention of the referees who are enforcing the rules, is a whole section on how my theory is more simple than any others, just in the same way that a section on how my theory is more beautiful than any others would be considered, well, that's nice, but it shouldn't be in a scientific paper, because it's not, it's not directly relevant to what the scientific paper should be doing. So it will be more like a passing remark, but a clever scientist will nevertheless make sure that readers notice this fact. And so when they themselves are thinking about these two theories, they'll notice that one of them managed to do what it did with far more frugal resources. And hopefully, if the readers value simplicity as much as the writer, they'll follow the writer's lead, in spite of the fact that the force of the argument cannot be actually passed through the literature itself.
Thank you so much for your answer, Professor. Thanks for patiently answering all of my questions.
Thanks, Tarun. Thanks, Tushar.
Yeah, so we have these anecdotal stories of Kekule, having a dream of snake, and then predicting the benzene ring structure, and then the apocryphal story of Newton's apple. So, do you suggest that the ongoing structure of science has kind of built a normative pressure on the scientists themselves to not tell their intentions, intuitions publicly, clearly, very lucid language, while we have this repository of anecdotal stories vis-a-vis science?
Why do we have these stories?
Yeah.
Well, to some extent, I guess it is a creation of a kind of mythology. Of course, I mean, just relating it to this talk, this sort of thing stands totally outside of official scientific argument.
Yeah.
But there is a certain tradition of a sort of a celebratory stories about the successes of science, I suppose. I mean, I'm not sure that I have anything particularly original to say about it. Just that perhaps when something is as complex in its workings as the process of scientific inquiry, it's important, if it's going to have good public relations in the outside world, to create a rather simple, perhaps oversimplified image of itself that ordinary people can consume and lock into without having to go through the complicated business of reading Popper and Kuhn, and hopefully my book as well, to find out how science really works.
Okay, thank you.
Thanks, Tushar. Any other questions that you'd like to ask? We have time for one or two more. Nothing right now. Okay, so maybe I'll take this opportunity to ask a question myself. And this is, I guess, how would you fit into this picture the fact that now a lot of scientific papers are starting to use Bayesian statistics, where at least seemingly the end product is a posterior probability? They seem to be making some claim of how much you should believe in the hypothesis given the evidence, even though the priors they're using may not be real priors, they're like ignorance priors or something. But at least they seem to be making a move that, according to your rules, is not really allowed, right? Yeah.
Bayesian statistics is not the same thing as Bayesian reasoning. So I think it still falls on the side of calculating some numbers that relate theory to evidence, but not the numbers that quantify evidential support. So a scientist will look at the calculation made in a Bayesian statistical setup and say, okay, what should I think in the light of that? and they'll still be importing their own plausibility rankings, as I call them in the book, their own subjective probabilities to actually make sense of what's going on. Still, this case does illustrate that, I said a little bit earlier, it's not that the quantification of evidential support itself is outlawed in official scientific argument. It's rather that anything that's ostensibly subjective is outlawed. So what can be brought in is anything objective, and that has the effect of leaving out typically evidential support. But if you find a stratagem, the right kind of stratagem, then you can do something that's like calculating evidential support. So you could do, you can construct an argument that has this Bayesian form. You can say, here's, as you just mentioned, here's, let's just take, as as I already said, a lot of what goes on is a bunch of assumptions are laid down, and then certain probabilities are calculated in the light of those assumptions. Here's something I can just kind of stipulate, supply as bedrock, as foundation. I put this prior probability distribution over my hypotheses. And typically, so this is when you're dealing with a big hypothesis space. You want to say something about all of these hypotheses at once. That's when you often use Bayesian statistics. So I'll just put this prior probability over it. But it's not that this is my personal prior probability distribution. There's nothing subjective about this. This is just a nice kind of probability distribution. We can all agree it's interesting to impose, and then we'll just calculate the probabilities in the light of that. That's a way of course, of edging closer to actually making claims about evidential support. I think the fact that the prior probability distribution has to be kind of basically introduced as a matter of convention is sort of means that we still can't really regard it as a genuine attempt to assess evidential support. But what it does do is when it's done in the right way, it conforms to the rule that is really the one that requires everything to be in some sense objective, or at least not controversial in any way. Does that help?
Yeah, but I guess more and more I'm getting the impression that this applies to really maybe just a subset of the official scientific communication, because maybe it's a more recent. So if you look at some of the classics of official scientific communication, right? Einstein's on the electrodynamics of moving bodies stresses the idea of his account being simple and consistent. If you read On the Origin of Species, he's constantly talking about the unified power of his argument, right? Is it just that was the old way of talking about things? Or is it that theorists still use those concepts in their work? It's just a particular kind of experimental literature where you don't see those concepts.
Well, I think those are actually quite unusual cases. The Origin of Species it's not clear that it's really, crazy though it seems to reflect on this fact. Nevertheless, it is the case. It was really written as a popular book, not as an official scientific paper. Although I do think it's also the case that these rules have been kind of refined and are enforced more rigorously as the whole system of peer reviewing and so on has grown up. Einstein also, I think, is an unusual case. I would say in the case of the special relativity paper, now I really need to go back and look at this. So I could just be wrong here, and it might just be that Einstein was, as I think he was in at least one of his other papers, really bending the rules. But I think there he's displaying the elegance and simplicity of his solution. He's certainly citing it as an inspiration for this view. He's saying, let's see if we can find a way of formulating electromagnetism in a completely symmetrical way. But he's not saying you should believe this theory rather than the Lorentz Fitzgerald theory, because it's simpler. And so he's not doing the forbidden thing. I think he came closer to doing the forbidden thing in his EPR paper on quantum mechanics, of saying really there's something that's just, I'm of course massively paraphrasing here, but there's something that's just intuitively wrong about this, never mind that it gets the evidence right. I think that really does break the rule. But that's exactly why scientists ignored that paper. They said, that's not science, that's interpretation. And I think interpretation was not the right way to characterize it. It might actually have been a pretty good argument, but it was the wrong sort of argument.
Okay, thanks. Mike, you have a question?
Yeah, thanks. Can you hear me okay? I'm using a different earpiece than usual. Okay, so I was wondering about the anthropology and the epistemology of the iron rule. And this is in the book. Forgive me, it's on the to read list.
That's fine.
I'm just sort of wondering, so anthropologically or historically, when does the rule show up? Did it happen before science splits into different disciplines, or was it more recent? If it was more recent, does it happen at the same time in all the disciplines? That seems unlikely. Are there some disciplines where the rule is less strict? So maybe qualitative social science, maybe it seems like it's a bit looser there. And I wonder sort of, why did that happen? Sorry, it looks like my internet's not great. And then the epistemological. Okay, the epistemological part, I guess, would be then, do you think that the rule is there because it makes just life simpler and more convenient for scientists, or is it there because it makes science epistemologically better?
Well, thanks. The story I tell in the book is that the rule arose in the scientific revolution. So at the very beginning of modern science, and really kind of makes modern science what it is. It was above all Newton's example that persuaded people to go with the rule. So Newton was doing science this way, very, very ostentatiously, and the scientists of the day, and of course it was in those days science was small enough that even people who were not doing physics were paying attention to what Newton was doing. That Newton was so successful in just focusing on the kind of predictive, or in the very shallow sense, explanatory power of his theories, and doing what he called the experimental philosophy, that basically everyone decided they would try doing things the same way. That's simplifying what I say in the book a little bit, actually, but at least it gives you the sketch of the answer to your question. So it did happen right at the beginning, and then as the sciences fanned out, they took the rule with them. And also, as I've said, the rule has tended to become more better formulated and better enforced. And there's still people who are in the. I think there is still a few domains of science that, or well, I guess they're not of science in a way because they don't follow the rule, but in the departments that have the names of science, like say cultural anthropology, I think in cultural anthropology, you find a lot of work that's just completely unconcerned with following the rule. It's just, so it exists in the anthropology department and the division of social sciences, but it's not driven by the rule. And this in the end, this is just the history of human thought. There's nothing about the rule that's inevitable, and so these things certainly can happen. But the reason for its ubiquity is, just as you speculated, that it was there from the beginning and traveled with science as science fanned out into all these specialties that no longer pay any attention to one another.
Okay, thanks. So we have one last question, I think, from Shinod, and then we'll close the session.
Hi. My one question has partially been answered when you talked about Einstein and EPR, but anyway, I'm posing it. So in the iron rules, you didn't particularly pay any attention at all, I think, to thought experiments. And theoreticians use it not only in their private thinking, but also it's available in the public literature of science. So where do you place that? Second one, not related, but the other one, if I understood correctly, the iron rules, you are saying that when people succeed, usually they follow the iron rule, but following the iron rule does not guarantee any success. It is not necessary that you will succeed if you focus on the empirical details of one particular small area of science. You seem to have said something in this line. So that gives a very bleak picture, meaning it's so scientific research seems to be highly risky. Then you're spending so much money and time and your career on something, but there is no guarantee. It's a real picture, but that seems to be a bit risky. I just would like to hear your comment on that part as well. real but quite risky an affair, given the iron rules.
Okay, can you? Okay, I'll begin with the first question. So I think science ultimately is driven by empirical evidence. Of course, that's a fairly mundane thing to say, but the evidence, there's not much use unless you also have theories. So a part of the enterprise of science, of this whole cycle of theory testing, is generating theories in the first place. One way to generate a theory is, or one step in theory generation sometimes is thought experimentation. And there's nothing wrong with that. Anything that's, the iron rule rules out a certain kind of argument in favor of a theory, or anything that's not an empirical argument in favor of a theory. But apart from that, it kind of doesn't mind what you do. If whatever inspires you to formulate a theory is in principle publishable. Often scientists would not choose to publish that stuff, and that might be considered something of a digression to publish it. But if you happen to report how a certain thought experiment had prompted the formulation of a certain theory, or to go back to the case of Einstein and special relativity, how a certain quest for symmetry had inspired you to formulate a certain theory, that would certainly not be breaking the rule, as long as you didn't claim that for example, your thought experiment was an argument in favor of the theory. Unless, of course, as with some famous thought experiments like Galileo's experiment about tying the objects together as you throw them off the tower. Unless, of course, what the thought experiment does is it actually exposes some sort of logical incoherence in the theory. It's certainly okay, although it's not how science mostly progresses, but it's certainly okay just to investigate. Well, no, I shouldn't have said that. It's okay and indeed important to investigate the logical and mathematical properties of a theory. It's not very common that you would discover that a theory is logically inconsistent, but of course, if you do, that's an important consideration, even though not an empirical one. More commonly, what you do in exploring the mathematical consequences of theory is discover, for example, some surprising new prediction your theory makes, like the wave theory of light, famously predicting the bright spot, and so on. And of course, that kind of enterprise is important too. So you could kind of think of, I guess you can think of there being three different related enterprises here. One is coming up with the theories in the first place. One is figuring out what kinds of predictions theories do and don't make, and given certain assumptions about phenomena. And finally, of course, the one that most scientists spend most of their lives on, actually conducting tests of theories in the light of those things.
Okay.
Then, was that enough?
No. I thought you would pause there. Yeah. So go ahead. Yeah.
I didn't say anything about the second question, but actually, it would help me if if you just formulated that question in a kind of a single sentence, just so I can zero in on exactly what you're asking me about.
Okay, it was like this. So to follow the iron rule means one has to pay attention to this a very minute or a very small portion of a part of science for a long period of time to gather the data, so to speak. You have two examples from the life sciences as well as from the evolutionary biology gives us this extreme focus on one aspect to gather the information. Along the side, you also seem to say that, but such focus may not always give us a success. So I was just commenting that this kind of paints a picture of science for an aspiring scientist, that this is an extremely risky affair, and there is no guarantee of success. But to succeed, you have to follow this pattern. But following this pattern does not ensure you any, not necessarily ensure you any success. So I was just because that part is a part which I like most in the book.
Okay.
Yeah, just a comment in that sense. Not
I see. Okay, great. Yes. Yeah. And I'm completely with you on all of that. Right. This is a part of what I tried to bring out in the book, and I am pleased that you enjoyed it.
Thank you.
Okay, thanks a lot, Shinod. So yeah, thank you very much, Professor Strevens, for being with us for so long, for the wonderful talk, and for engaging with us for so long. And thanks to everyone who attended and for the questions you asked. We'll see you all tomorrow morning for the next session. So yeah, thanks very much.